Hello, the countdown clock has begun counting down, so I'm going to begin. This is my talk on smart pointers. The original alternate title was a clickbaity title for an interesting problem. I came up with an alternate title instead. If my, good technical problems. One moment. There we go. So we're going to fix lifetime issues with this one weird trick. And fix is, of course, in air quotes because nothing is a perfect fix. So my name is Matthew Fleming, like the title slide said. I work at Pure Storage, and I want to spend a brief moment explaining the kind of stuff I work on. My experience is that talks make a lot more sense, and I can relate to them better if I know what problems the author is trying to solve, because they may not be my problems. So what I work on happens to be in C++11. We have finally gone through the rototilling we think we can switch to C++17 early next year. We are somewhat multi-threaded in that we have like 8 to 64 threads, roughly. One thread per core. So we're not like massively multi-threaded, but it's not like it's super tiny either. Our code is almost entirely lock-free, hopefully wait-free most of the time. It is almost entirely asynchronous code using a homegrown asynchronous programming framework that happily looks almost identical to a manual stackless coroutine system. So I have high hopes that I can relatively easily transition in a layered way to using actual C++ coroutines sometime after C++20 ships. I work with about 100 other developers on a 1.3 million-ish line of code base. And the developers I work with, they are not C++ experts by any means. In fact, many of them don't know C++ when they come to work for us. And they're also, in addition to being new to C++, they're new to asynchronous programming. They are new to thinking about lock-free programming. They are new to flash storage, which is what we work on. They're new to template metaprogramming because they've never seen C++. They're new to file systems. They've never had to think about NFS protocols or snapshots or anything like that before. And giving them good tools, good software tools, so they can think about their problem, whether it's snapshots or replication or protocol layer things, and not have to think about the nuts and bolts of C++, that's really critical for us, and specifically for me, because I'm one of the people who helps maintain our internal libraries. And this is low-ish latency flash storage. It's not low latency like high-frequency trading, but we're still looking for, in our case, 1 to 3 milliseconds for things that involve going across network connections. So this is a clickbait title because that's how you get people to come to your talk. But there is no silver bullet. We're not going to be able to fix everything. And nothing that's being done here is magic. It's really a set of both software tools and mental models. But I think we can make things better than the existing state of the art or state of the world. And this is going to be done through incremental improvements the same way shared putter and unique putter were an incremental improvement, albeit a big one, over previous smart pointer systems. I will probably say some controversial things, in which case better is in the eye of the beholder. This happens to be my hour, so my opinions are mostly correct right now, but I'm just a guy. And I did give a talk at C++ Now called an alternate smart pointer hierarchy. I focused in that talk a lot more on some interesting alternative owning smart pointer semantics. And so I'm going to focus in this talk instead on non-owning smart pointers. But there is a link there to the YouTube talk if you want to check that out at some point. So my first thesis for this entire talk is that none of these coding tools are actually needed. That is, you can write 100% correct C++ code, maybe modulo exception safety, using raw C++. And so every single one of these tools that we add has to add significant value. Like Chandler Carruth was saying in his talk, there are no zero-cost abstractions. These are abstractions with a mental cost, hopefully not an actual machine time cost. And so they should add to our understanding of code and not be more costly than what they give it to us in benefits. A few quick definitions. When I talk about lifetime errors, this is in general using a pointer or reference when it isn't actually pointing to what you thought it did. This can cause a memory corruption. It could, which sometimes people think the word corruption is scary, so we call it scribbling instead because it's a rose by any other name. And a lot of times actually your code just works. It just depends on what has gone on with the thing you used to point to. Did it get freed to the system and then the allocator hasn't bothered returning that memory to someone else, and so the bits are all still the same? You can get a double free. This is when you free the same address twice. This sort of thing can easily cause other lifetime errors because the memory is reallocated for somebody else. It can cause your allocator to get corrupted. It could cause your allocator to crash if it has decent debugging, or it may just sort of silently work for a while. And use after free is a very similar thing where you're using the pointer after the underlying memory is freed. This doesn't always have to be because of a double free. There are other reasons, but it's another category of lifetime error. If you're lucky, that's a seg fault. If you're not lucky, something else happens. So we can use tools to detect a lot of these things, and I'm not going to talk about those tools because tooling is really nice and it will help a lot, but it is not perfect. I love ASAN. It finds a lot of interesting bugs and it gives me really useful information about what actually went wrong, but it can't actually catch a timing race until that race happens in your code. So if you have very rare races or very small timing windows that never happen to occur in your ASAN run, the tool will not find that for you. Static analysis is also really nice, but it has some knowledge of what it thinks are memory lifetimes and other things going on, but it can't know everything you know. And in some sense, it either has to give you false positives or false negatives. Testing is nice, but again, it can only find the issues that your tests actually cover. If you have longer running test cases, very rare events, you're not going to hit your actual bugs very often. And so in the end, reading code is the only thing I actually trust, and then convincing myself through reading code that all of my uses of memory across asynchronous boundaries is actually correct. And since I trust reading code in the end as the final answer to whether something is correct, I want reading the code to be as simple as possible. So this is the first guideline I have, no owning raw pointers. We've been talking about this for a while. You've got shared putter and unique putter, and we've been saying you should use those for a while. So this should not be a surprise to anybody, I think. You might wonder, can you ban the delete keyword entirely from your code repository? And the answer is maybe. There are reasons why you might need it. You may need a raw pointer that has ownership because you're using a pre-C++ 14 lambda where you can't move things into it. You may be using atomic updates on some state where you can't have a move-only type in it because that doesn't work with atomic updates unless it's the simple case like a single shared pointer. But using smart pointers like shared and unique pointer, they do at least fix our memory leaks due to a missed delete. And so it makes it harder to have a double free, but not impossible. So along that line, here's 4 lines of code. Every single line is incorrect. Every single line compiles. So you shouldn't do any of these things, obviously. Probably the only thing that's actually going to crash immediately is that 4th line because you're deleting the actual thing that's probably on your stack, not the underlying memory. So these are, you might look at this and say, yeah, that's clearly wrong. But when you get longer pull requests, when you get buried in a mess of code, it gets a little bit harder to tell. And I'll go back to this in a bit. So I'm going to slightly modify this guideline based on my experience. You want to see maybe almost no owning raw pointers because there are exceptions, I think. So delete's maybe not a bug, but it should be really rare in your code. And so each of the very small number of instances of the keyword delete in your code in a perfect world should be obviously correct, and it should be very tightly constrained to a small module that you or some other person who understands how to write libraries wrote, and everyone else just consumes from the outside. And in fact, in some sense, this is exactly what shared and unique pointer are. It is a library written by somebody smart that you only use from the outside, but inside it still has to do a delete. Okay, so this is an example of code that is, this is slideware, of course, but this is very similar to something that actually showed up in our source code at some point. And this code is buggy, and it's not necessarily obviously buggy, and the bug that this caused took us 2 months to track down. And the reason it took 2 months to track down is this particular code path would hit maybe once a day on only some of our toughest test beds that were running more interesting HA tests, more failovers. And the problem is, of course, this buggy line of code wasn't where we crashed. We crashed later when we did the thing that was actually correct. And we had maybe 200 or 300 instances of this kind of notification callback in the system, and it's hard to go and look through all of them to figure out, is this one right? So as you can maybe tell, the problem here is that this error object is being passed as a non-owning pointer. But the type system doesn't tell me that. It was by convention. Now, we'd never had a single instance of this where this was an owning pointer, but that didn't stop some person at the company who didn't know that that was the convention from thinking they should take ownership. And the person who reviewed their code also apparently didn't know that convention and didn't see it in code review. And so this happened to us once, and then we fixed it. And then maybe a year later, it happened to us again. So this code's buggy, and you might say, great, we won't have delete in our code base because we now have owning smart pointers for everything, and we'll use raw pointers to mean non-ownership. So you ban the keyword delete, and your enterprising developer instead writes this code. And they very helpfully explain their reasoning in a comment that is 100% wrong, but feels right. So this code will also compile. It'll do exactly what you don't want. And again, it may not be spotted in code review. So this code, using a C++20 feature I'll cover in a moment, this code, it won't compile to actually take ownership of this resource. We've been explicit through the type system that I am observing this error, I am not owning it. And so I can't, without typing a lot more characters, accidentally take ownership and do the wrong thing. We pushed through or changed to our code base about like this. It took me 4 weeks working on it on and off because there were literally hundreds and hundreds of sites that I had to fix and then verify that I didn't break anything. And I think the first attempt then ran afoul of something weird where the optimizer didn't like the code quite as much, and so we had a small performance regression and had to back the whole thing out and then stare carefully at assembly and then fix it again. But it was definitely worth doing because we will never see this bug again. And that's nice because I don't want to waste a month of my life debugging it ever again. So my second thesis then is being explicit is better than being implicit. The bug we ran into is because we had this implicit idea that we were non-owning. And if I can just be explicit about it with a little bit of help from the type system, it makes it harder to actually type bugs because they won't even compile. So guideline number 2, no non-owning raw pointers. We have observer putter in C++20. This is definitely an improvement over using raw pointers. In my experience with the code I've had to deal with and the current proposed API, it gets me about 70% of the way to solving the problem I want, and I'll cover that also. And unlike your owning pointers, where there may be special circumstances where you can't convert an owning pointer from a raw pointer to a smart pointer because of move-only semantics, you actually can or should be able to convert 100% of your non-owning pointers to using this kind of observer pointer. And so, because you can always get the raw pointer back for legacy APIs, and it's trivially copyable and assignable, so it should flow through your code much more like a raw pointer does. So, thesis 3 then. These smart pointer types work best when I have less code to change. So just the way like a raw pointer, I just pass it from function to function and it happily compiles and it just moves along. I would like these owning and non-owning pointers to flow trivially through my code. I shouldn't have to do a lot of conversions to go from owning to non-owning and from non-owning to raw pointer if I believe, well, I should have to do some to make it go to raw pointer, as I'll cover. But I'd like them to flow more trivially through my code. So this is, let me give you a brief for those who don't know. This is, slideware version of observer pointer. I'm ignoring public and private and other things, but essentially there's just a single member, which is the raw pointer. I have a explicit constructor, which will take in a pointer and assign, put it in. I have a defaulted copy and move constructor, defaulted copy and assignment. I have a conversion from some other kind of observer pointer with a different templated type as long as the types are convertible. It has release, reset, bool, get, arrow, and star, and other utility functions that match unique pointer. And this is one place where you might, where you as a user of this might have disagreements with the C++ committee about what's a good idea. And the thing is, for example, release makes a lot of sense on an owning pointer because it owns a resource, I would like to release it, and so it should give me back the raw pointer to do something funny with and reset itself to null because otherwise that is a double free. For a non-owning pointer, that function, the semantic of that function isn't as useful. My assumption, having not participated in any of the deliberations, my assumption is that that's here because it will match a owning smart pointer, and so you can do more generic programming. There are probably good reasons for that. It also sometimes maybe seems like a bad idea to me in that if I'm doing generic programming on a thing I think is an owning pointer, I might actually do different things than with a non-owning pointer. And so the existence of a function like release may make me think I have to do a very specific thing with it other than hopefully just shove it right back into the type it came from eventually. So is this sort of clear to people what how observer pointer is kind of implemented under the covers? All right, I'm seeing nodding. So one problem I personally have with this in terms of ergonomics, there's no implicit conversion from a unique pointer or a shared pointer into observer pointer. I have to stand on my head a little bit to create one of these things. And that makes it harder to craft correct APIs. Because in some sense, the whole point of having a non-owning smart pointer is that if I'm explicit about ownership and non-ownership, the type system has already protected me from accidentally creating double ownership when I shouldn't. I can easily make it not compile when I don't want it to. I can't get raw pointers back out easily. So why should it be hard to take something that has ownership and trivially create something that doesn't have ownership when I'm actually now being explicit that I don't have ownership? In my mind, this makes it just harder to use the code. But that is a good question, though. Should you be able to trivially get a non-owning pointer from an owning one? And this is, again, a place of tension, perhaps, between ultimate safety and convenience. I have a little bit of example code there. The idea is here, I probably don't have this kind of overload set. I would not have a function that both takes a non-owning pointer and takes a reference to an owning pointer. And in fact, I probably wouldn't often write a function that takes a reference to an owning pointer because the question then is, what am I doing with it? I'm not transferring ownership. I'm saying, here you can have it, and maybe you can fiddle with it, but I'm not really giving it to you, but you might take it anyway. That's sort of a weird thing to do. And if it's something that should be filled in like a return value, that should probably be a return value. So it's a weird thing to have. And so then I would like this code, lines 4 and 5, I'd like that to just compile and work. Because I have something that has ownership, but I don't need to know it has ownership to know that calling that function is safe because the type system already protects me. The same way the type system protects you from making mistakes with, if you have enough warnings and other fiddly bits, it prevents you from making mistakes with longs versus ints or longs and doubles, etc. You get some protection from the compiler against screw-ups. Which overload do I want to call? I do not, well, so if I had both, it will call number one but I don't think number one as an overload should exist. Sorry, that was the question was which overload should it call, if that wasn't clear from context. Okay, so here's one of my possibly controversial statements, harkening back to Dijkstra's considered harmful. So is .get actually even a good idea at all? And in 2011, I would say yes, it definitely was, right? I was in a world in 2011 where basically everything was either raw putter or auto putter, neither of which I really wanted. And so I have some now pretty decent owning smart pointer types, but I have a lot of legacy code that wants a raw pointer, and I probably don't want to have to do a lot of typing to work with that code. So .get is relatively short, and it's pretty convenient, and so it works. The trouble, I think, is now it's another 8 or 9 years since then, and hopefully a lot more code bases have moved toward this world where this ownership is more explicit. And if I make it easy to get back a raw pointer, when my whole idea of my system is that I shouldn't have raw pointers, I feel like I'm going backwards. So in some sense, as a design point for the non-owning smart, actually for any smart pointer that I want to work with long term, I actually want to make it really hard to subvert ownership. And getting a raw pointer back from either an owning or a non-owning pointer makes it much easier to trivially create unexpected, incorrect ownership. And I will have some examples of that later also. So here, I've got a legacy function that takes a raw pointer, and I'm calling it 4 different ways. Every single one of these will compile. Which one of these looks like a bug? Or at least, which one of these looks like a thing that if you saw it in a code review, or when you're trying to chase down a weird memory corruption error, which one of these lines of code would you actually look at and say, dang, that's probably not right? So my argument is, yeah, so number 2 would look funny, right? Because ampersand star, when I start putting symbols together, I'm probably doing something weird. My argument is number 1 doesn't look very scary. And that's what the state of the art is today. At work, because we have our own smart pointer types at work because we started the code pre-C++ 11, and it existed long enough before we got 11 compilers, we're not going to change. And we're actually going through the process of removing .get from our smart pointer types entirely. And the function name we came up with to replace that we called raw pointer ignoring lifetime, because it's a mouthful. It's a lot of letters to type. It is not convenient, it is not ergonomic, and it looks scary, and it tells you exactly what it's doing. By the way, if you type number 4, you should really rethink your decisions. So I mentioned the implicit conversion from an owning pointer to transition to non-owning, because as long as it's hard to go from non-owning back to owning, that's a safe transition. It should be easy, in my opinion. I would actually also like it to be trivial to go from a raw pointer to a non-owning pointer. It can't be, in some sense, it can't be unsafe, because if I've made it hard to get the raw pointer back from this non-owning smart pointer, it's safe to go from a raw pointer to a non-owning smart pointer. I can't accidentally turn it back into an owning pointer, whether it should have been or not. So, and if I don't have something like this, it makes it very hard to pick a place in my code base where I start converting from non-owning raw pointers to non-owning smart pointers. Because wherever I pick, I have people above me or below me, and I have to do something inconvenient to get back into the legacy functions I haven't converted yet. So we can't implicitly convert from a raw pointer. Maybe we'd like to, but there is a reason not to, of course. So for one thing, the explicit constructor from a raw pointer matches that of shared and unique pointer, where it actually makes a lot of sense. I should be very explicit that I'm taking ownership. But there also could be, if your code is like mine, you have some factory functions, and you lived in an old world where factory functions returned a raw pointer, and they just had a comment saying, yeah, you need to take ownership of this. And that's, the comment's all cute and all, but the type system doesn't help me. I would actually like that owning raw pointer to not implicitly become a non-owning pointer, and that actually turns out to be really hard. So the prototype that I showed for observer putter took a raw T star, and it would be really great if I could type something like those bottom 2 lines, where I could take well, actually I can type those 2 lines, but it doesn't quite do what I want. So there's a couple ways to construct this, none of which actually works, as I discovered last night when I was putting examples up on Godbolt. So what I want is to implicitly convert a const reference to a raw pointer, because that's a value type. It's an L value, and the L value means it's already inside a raw pointer. And if it's already a raw pointer, that's great. And I would like to not convert from an R value of a raw pointer, which is a thing you can type, and I didn't know this until I started working at this job. It's a thing you can type, the type system's happy. The problem is that that doesn't end up working. If I make it explicit, I will never select that overload unless I'm actually explicit. In the implicit context, the compiler will say, well, you didn't say you wanted this one because you weren't explicit, so let me see if I can convert to any of the other constructors. And it can implicitly convert an R value reference into a const L value reference. That's a safe conversion according to the type system, as best I understand. I could say equals delete. That does do what you want, because I'm not saying explicit, I'm just saying you just can't make an owning pointer, a non-owning pointer from an R value raw pointer. The problem is that doesn't let me say some other things I want to. Because, for example, ampersand foo is actually an R value of a pointer, and then I couldn't pass the address of a local variable as a non-owning pointer, which is clearly something I'd like to do, I think. So I don't know how to solve this problem exactly. You could argue that maybe I don't need to. The fact that this is a non-owning pointer means the worst that happens is a memory leak, which is better than most alternatives. So that's, in some sense, the end of what I'm going to talk about pointers themselves. And I'm going to move on to references, because in a lot of ways a reference is just a pointer. It's just got some syntactic goop around it and a small assumption that it's probably not null. You could say it's definitely not null, except that you can construct a null reference and you can't check that it's null, because the compiler will actually omit your code under optimization, because it knows the address isn't null. It's a reference. So I've got 2 functions I'm calling, local variables foo and bar. Which one of these 2 functions could modify its arguments? Right, we're C++ programmers. We actually know that both of those could modify their arguments. Great. That's troublesome, though, because one of them kind of looks at first glance like it doesn't, and it looks identical to code that doesn't mutate its arguments because the prototype says I'm taking by value or const reference. So Google's style guide will tell us that we should prefer return values over out pointers or output parameters, but if we do have an output parameter, we have to pass it by pointer. And that's to make that issue explicit in your code. You've made visible that you are possibly mutating the input. Bloomberg's style guide goes even further. Not only should output always be passed by pointer, not by reference or any other type, inputs, where the address is going to be retained past the initial function call, must also be passed by pointer. And that solves, again, the problem that you thought maybe you passed a value, maybe you didn't, but the code underneath actually is holding on to a handle to your memory past the time when you think it could be done with it. So this is, again, about making explicit, but instead of making explicit what can be mutated, this is now making lifetime explicit by saying, in our style, you have to pass by pointer, not by reference. And so I find it interesting that more than one company has decided that passing by mutating reference is maybe, it works, but it's unclear. So now that we're thinking about maybe asynchronous programming, lifetime errors, which one of these two lines of code could segfault? So both of them could segfault unless foo is actually a value, not a reference. If it's a value, then that can't segfault because it's just a structure member. It's just, I've got a valid address, I'm bumping it up by a little bit. Which one of these can segfault? Again, the answer is it depends. If foo is a reference, they both could. If foo is a value, only one of them will. Which one of these two can see garbage data? It's the same issue. Again, it depends on the type of foo. The trouble I have with this, and the thing I get, the reason I like those style guides is because this brings up what I've been calling non-local reasoning. I haven't seen this term used elsewhere. If someone else has a word for it, I'd love to hear about it. The idea is, the further away from a line of code I have to go to actually find the answer to my question, the longer it takes me to debug things. It takes more mental effort. I have to, instead of scrutinizing 3 lines of code in a function, I have to scrutinize almost every one because I'm calling functions and I'm passing things that maybe they're values, maybe they're const references, maybe they're mutable references. I can't tell from the call site. And so maybe I've got an IDE that's helpful, or maybe you're really old school like me and now you're doing git grep and looking in cscope and hoping that you found the right overload and stuff. And so I think it would be really nice if we could start being explicit about this sort of thing. I have one more point on that. I think I'm going to repeat it later. But the other point about this is when I have those references, foo.bar, that could be a cache miss, pointer dereference or something, or it may not be. Foo arrow is always one thing. And I would really like it if one way of saying things couldn't mean 2 things. Because I think that's where a big part of the mental burden comes from. I have one way of saying things, but it actually means 2 different things depending on context, in a sort of a different way than overload sets mean different things. Because a good overload set actually means I do the same thing every time. It's just the input's maybe a double or a float or an int, but I'm actually doing the same underlying function. In a well-designed overload set, that is true. So when you get to asynchronous programming now, it's going to change our understanding about lifetimes. When you're thinking about synchronous programming, whether you pass by value, reference, const reference, at least from the scope of the function you call, everything's still good. It was good when you called the function, it'll be good for the entire length of the function. And the moment I get to asynchronous programming, everything changes. So this is a slideware because you would never write code like this, but I think it's illustrative of the example. I have this function slow accum. I take 2 inputs. One is actually an input, one is an output parameter. I have hopefully named the parameters such, but the type system tells me nothing. And so I'm going to accumulate the sum of the size of everything. And meanwhile, I'm going to co-await in between each one. I'm going to very slowly accumulate these things. Maybe it's a much more expensive computation, and I want to be very friendly to the CPU. And I just want to say, look, I've done a bunch of hard work. Somebody else can have a turn. This is not coroutine syntax. There's still some debate about that. There are people who want the async keyword or something like it to be a part of the prototype and function signature, because otherwise you can't tell a coroutine from a non-coroutine without looking at the implementation and scrolling down however far it is to find your co-await or co-return keyword. So I'm using a non-existent syntax. So building on this then, especially when thinking about asynchronous programming and the other issues, I don't actually think references are all that awesome. They solve an absolutely fundamentally necessary problem in the language. I cannot have an operator square brackets that works without references. It's the only way to make that work in a way that syntactically makes sense. But they make all of my calling code harder to reason about. And when I have a reference versus a pointer, I have two ways to do one thing. And they're fundamentally different only in the idea of whether something is null. But null is only one of many kinds of actual memory or lifetime error I will eventually be concerned about. And so I don't, in my experience, that null versus not null has not been in my list of, if I have top 3 list of bugs I worry about, null pointers are not in the list. So continuing on then, consistent code is great for lowering our cognitive load. And so if we pass by pointer to indicate these concepts, I'm now more consistent. The language doesn't require me to do it, but I could have the discipline to do it for myself as a gift to my future self who is woken up at 3 a.m. by the pager and needs to really find an answer fast. And especially for asynchronous code, actually, passing by pointer or by value will completely clarify my lifetime issues. If I always pass by something that's a value type, I don't have lifetime issues anymore in this, because I now have assumed ownership of everything that I need. It's now a part of my coroutine frame. So here's my original example. I'm going to apply Google's style rules to this, and I'm going to say, great. I'm going to pass that first input by const reference because it's not mutated, and I'm going to pass the second one by pointer. And so now I've actually got some very obvious dereferences in here, and it might be more obvious that if I had a lifetime bug, it's somewhere in there. And then they can apply some smart pointer guidelines and to say, great, it's not a raw pointer, it's an observer, and the only thing that changed was the API. My source code didn't change. And I have this helpful document here that the output can't be null, and since I don't have contracts yet, I'll get to that in a moment too. So now I can apply Bloomberg's guidelines, and I say, great, that input actually effectively has its address maintained after the initial function call. This is a coroutine. I'm going async. I'm effectively holding on to that address past when the initial function returns. So I should pass it by pointer to make that clear at the call site. And the only thing that changes in the implementation is I have to use a star in order to get the underlying thing. And so now we'll apply the smart pointer guidelines again, and we'll say, okay, great, that shouldn't be a raw pointer, it should be an observer pointer. And the code didn't change, just a function prototype. But now I've got this different problem. Almost everything I'm inputting is now an observer pointer, and I've lost a bunch of meaning. So I've got references which mean things are never null, and now I'm passing by pointer, and it's observer pointer, but it's still nullable. And so you might ask the question, would something like an observer ref, would that make sense as an additional type? It's almost exactly like observer pointer. We could imagine such a thing. You still use operator arrow and operator star to access the underlying memory, so my uses of it look a little scary. They look like they could be a bug. But I have some guarantee by an actual contract that it's never null, and I can actually get this checking from real contracts or from debug asserts in a way I can't quite get with references. And then suppose I had this thing, I have another decision point about it. Should I allow constructing one of these things from a raw reference, or should I require a pointer? And that leads to slightly different code where either I look more like a C++ reference, and so maybe my code changes less, but maybe now I'm hiding mutated parameters or lifetime issues again. So this is a design point. If you wanted both an observer pointer and an observer ref, you would have to think about. And in fact, I have more than just this. In some sense, I have two kinds of by pointer inputs. I have these inputs that are output arguments, actually. And I might want to name like out and out opt for optional ones. And if I don't have stood optional, maybe stood optional of out would be good enough. Or in out for something that's an in and an out argument. Output args are almost never null unless they're optional, which is relatively rare. It's rare to call a function and say, put the answer here, and not give you a here to put it in. That would typically be an obvious bug. Unfortunately, C++ doesn't let me make a write-only type. I would really love it if out was something I could only store into, but I couldn't read from. But operator star has to return a reference, and once I've got a reference, I can go both ways. And then I have what we call in our code base, borrowed pointer and borrowed ref. These are inputs, essentially. They are non-owning pointers. They preserve a little of your pointer versus reference differences, but by contract, I can't have a null ref. And so this is sort of maybe not quite an eye chart, but I have this taxonomy now of things where I might want to think about whether they can be null, what their asynchronous lifetime would be, and whether I can default construct them. And so the idea in perhaps this new taxonomy would be that borrowed ref looks just like a reference. It's got the same lifetime ideas, it's got the same ability to not be constructed from null, and it has the same idea that I can't default construct it, and maybe I can't reassign it either. And similarly, borrowed pointer should look exactly like a raw pointer, and out and in out are sort of in the middle ground. There's an implicit semantic for an out pointer that it better last as long as whatever asynchronous code you're calling, or you as the caller have already screwed up. Like I shouldn't have to say anything about this is unusual about the lifetime. If you've told me to fill in a value and it's going to take me a while to compute it, and I'm going across asynchronous boundaries, if you didn't give me something that'll last until the result is actually ready, that's your bug, not mine. And so I have this implicit difference in understanding of asynchronous lifetime between what I might call a borrowed pointer and an output pointer. Okay, so I have a little code example going through essentially the implementation we have at work. I'm not going to spend a lot of time on this. The link is in the slide. The slides will be up on wherever the slides go in another couple days when I email them. So the basic idea is I've implemented this function raw pointer ignoring lifetime. I forward declare it so I can make friend functions, and there's some fiddly bits here about tagging versus reference versus pointer. This is mostly fun normal smart pointer syntax. I can assert that you didn't give me null things on construction. That's nice. I can say things like I can statically assert that you don't construct a referenceable type with a null pointer. That's kind of nice. I get that same kind of thing from a raw reference. I added some comments about possible semantics here. The point of all this is that once you scroll down through a bunch of, it's still kind of slideware, you get down to a bunch of code that actually uses it. And I've commented out, so I've got this sample use site. I take a borrowed ref and I just print it. It's not null, I don't have to check. And I've got a bunch of sample use sites. I could construct a borrowed ref from a unique, and it just looks safe and simple. I can't reassign it, that line won't compile. I can pass a borrowed ref or a unique putter or the address of a pointer. I can pass all of those things and it just compiles. I don't have to do any extra typing. I did find one surprise here. I'd love it if someone can explain this one to me. So borrowed ref, I don't want to construct it from, one of the parts was I don't want to construct any borrow type from an R value of an actual owning pointer, because you're trying to say, here, take ownership, and my type literally says I can't own things. So there's, I've just completely deleted those constructors. And so if I explicitly try to create one here, that fails. And if I use the assignment syntax instead of construction, this compiles. And I can't figure out why, because the assignment operator also doesn't work, I don't think. Maybe I didn't get rid of that one. But I can't reassign into borrowed refs anyway, so I'm not quite sure what overloads this is calling. And if somebody knows the actual concrete difference in which special member functions are called when you construct by like this style or this style, I'd be very interested to hear that later. So I have some more examples of things I can and can't do, depending on, these are using slightly looser semantics about ownership, where, yeah, you wanted a std move, but I'm not taking it, so maybe that's okay. The other point here is observer putter. I can make an observer putter by explicitly using .get. I can be explicit about passing in a raw pointer and get an observer pointer. I can't just initialize it like this, that doesn't compile. I can't assign it using anything other than another observer putter, either from a smart pointer or not. And I can't delete it, which is good, but there's a lot of things I can't do with it I kind of want. And then here's some things that do compile, which should compile because you were very explicit about doing something dumb. And more things that don't compile, I can't delete things. So this is out there if you want to look at it more and play a little bit with explicit versus implicit, what's deleted, what's not. So using a slightly broader taxonomy of smart pointers, this is what my original example might look like now. I have a borrowed ref for the input, and I have an output. And the only thing I have to document about this API now is that for this specific use, the input must have a lifetime longer than the async function. That's a requirement of the API. I cannot put that in the type system. My static analysis tools could quite possibly tell me, this is an async function and then the lifetime is not long enough, but that's not a bug necessarily, because I may know more things about lifetime than the static analysis tool. it's, I think, probably provably correct that you can always know something this tool can't know. That's technically correct, just hard to analyze. And so I'd call this function essentially like we would before. I pass in an address of account, and following Bloomberg's style rules at least, I'd pass the address of the container I'm iterating over. So, so a third guideline then is consider at least only passing by value to an asynchronous function. Pointers and non-owning smart pointers, those are values. Your function definition should be using the appropriate kinds of smart pointers to encapsulate meaning. Supposing I don't actually have the standard committee give me out and out and all those other names, I might just be able to make a using alias that works well enough, or I could make my own type. This is actually another point of interesting tension. I, as a consumer of these things, with a relatively limited audience and a relatively narrow domain, I might want slightly different guarantees and behaviors than what the standards committee could give the broad community of hundreds of thousands of C++ developers. Because the things that are to me not a bug may be considered sketchy enough to the committee that they don't want to make them easy to do. And the things that are considered to me a bug, like .get, may be considered by the committee as we want to be consistent with existing types, or it's going to be 20 years before people finish rototilling their code bases, or whatever reason. So I think there's this sort of natural tension between what is appropriate for standardization and what you may actually want in your code base. And that's sort of unfortunate, right? In some sense, I can't get by the standard exactly what I want. It's either too specialized or too constrained or something like that. And you just kind of hope that it meets your purpose well enough that you'd rather use standard tools than roll your own. The other part of this guideline 3 is we should be explicit about lifetime if the type isn't. For any asynchronous function, I have to really think about lifetime. Values are good, anything else is possibly sketchy. And I should have this assumption, I think, that something that you would think of as an out parameter has a long enough life, and any other type of borrow parameter is only good up through like the initial invocation of the function call and up to the first moment you go async. Because technically that's all you get. If I'm giving you some kind of borrow type, you don't know where it is. It may be gone by the time you return to your coroutine frame. And it's important to remember that things like span and string view, these are also borrow types. There's no ownership inside them. I'm passing them by value, but I still have to think about lifetime on these types as well. So you're in this world, you've got a code base, it's a lovely code base, it solves your problems, but you'd like it to be a little more strict about types. How do you get there from here? My experience has been that you want to fix your owning pointers first. If you have a raw pointer that actually expresses ownership, that's much more dangerous than a raw pointer that doesn't express ownership. You can have bugs like the one I showed at the beginning. They are relatively rare. If you're able to run your full production code in an ASAN environment, the address sanitizer will tell you who did the bad thing and then who tripped across it. So any kind of owning pointer is better than a raw pointer in my experience. And at least in our code base, almost every instance that was using one of those legacy factory functions that returned a raw pointer, it was immediately holding the value in an actual correct owning smart pointer. It's just that the API hadn't been changed. So most of the changes I had to do to fix those up were just to change the API. I was returning a new type, I fixed up the implementation. I did not have to change the calling code because I was already taking ownership. Your code base may not be like that, but in the process of converting raw pointers to owning pointers, you'll probably find some interesting places where you might want to worry about lifetime. I would say you also want to at least consider not using .get. The library gives it to you. Maybe you would just say, look, we're not going to use .get. We're going to implement this raw pointer ignoring lifetime function. It's pretty trivial to implement. And the nice thing about that is twofold. Number one, it gives you a really scary name. And number two, it actually makes it really easy to grep for sites in your code where you haven't pushed through all the properties of explicit ownership and non-ownership. You now have a .get's really hard to grep for. Maybe you've got a tool that can show you these things, but it's really easy to grep for that function. And in fact, I sometimes just kind of grep that against my code base to see if somebody thought they were being clever solving their problem and actually shouldn't have done that because they didn't understand how to properly use owning and non-owning smart pointers. So it's also easy to find sketchy code someone else wrote that I never was on the code review for. I like to check that out occasionally. You do find real bugs that way. So essentially to summarize here, I had these 4 theses. You can write 100% correct code in raw C++, so we should add value with any of these new types.
Being explicit's better than being implicit. All of these types will work best if I have less code to change. I'd still rather be explicit and type more, but I'd ideally like it so I can not have to type much and let the type system give me belief about correctness rather than having to explicitly say, yes, let me put it in an observer pointer now, yes, let me do something else. And finally, references have some issues, especially when you start thinking about async code. They are no longer the safe thing to do in some sense. And by moving away from references to appropriate non-owning smart pointers, I actually can clarify my code. I can now make it easier to tell what's mutated, what's not. And so these choices for your smart pointer semantics can make your code easier to read also. How much do you have to type to make it happen? So the guidelines were relatively simple. No owning raw pointers unless you have to. No non-owning raw pointers. It's going to take a while to get here. I think I've been working on this in our code base for 3 years on and off, and I'm maybe 2/3 of the way done. I don't know. It takes a while. There's a million lines of code, and so you fix the low-level stuff, and you kind of bubble out towards the outside. You tell all your tech leads, hey, please start typing the new hotness. And the new hotness, if you do it right, integrates well with the old stuff. So like, I don't have to, like, all the code I'm used to typing for callers doesn't get different. It's just the API and the implementation, and that's pretty trivial for people to remember to do. And then remember to pass by value to async code, and if you are not passing by value, be explicit about lifetimes. That's the end of what I thought I might be able to fit in time. I have a couple small appendices that it looks like I have a bit of time for. So one thing I wanted to mention, if you have owning smart pointers, you can still end up with a double free. And it's really not that hard, but it does rely on multi-threaded code. So I've got this multi-threaded member function. I happily have a owning smart pointer as a member, and I very helpfully reset the buffer early because I don't want to hold on to resources longer than I have to. And this is probably code I should write sometimes. I mean, if it's going to be a while before this type is done, but I'm done with that memory, it might be nice to free up the resources, especially if it's something scarce. But you probably can already recognize I've got a data race here if it's actually multi-threaded. Whereas in a destructor, I would not have had the data race. Destructors are guaranteed single-threaded. The world is nonsensical otherwise. So there's a data race there. I think the next appendix is a little bit inscrutable in the time I have. So if you want to see a brief but slightly hard to read example of why you might need an owning but raw pointer, I have some code for that I can go over, but I think right now is a good time to open for questions.
So hello, thanks for the talk. So what my question is actually, or like discussion start point, from my point of view, it feels like I would like to disagree on the observer pointer. So first of all, if you remember Chandler's talk, every abstraction comes with a cost.
Absolutely.
And you gave us the example where you had the convention that a raw pointer is a non-owning pointer, and someone constructed a unique pointer from it, and then the unique pointer again caused the non-owning pointer to be deleted. But actually, for me, it feels like if you have that kind of like the reasoning that was in the comment, that he could also apply to the observer pointer. He could just call get or the scary function and then create a unique pointer from it and then delete it again. And you said this kind of bug is quite, it's not very common in a code bases, right?
Which part is not common? I don't remember exactly what I said, but explicitly calling delete when you shouldn't or something like that, I haven't seen much, but it takes a long time to debug. So my experience has been it's worth a little bit of time to make that bug never happen again. I mean, we literally lost months of engineer time trying to debug that.
And with make unique, you could even go ahead and say, maybe we should remove the constructor, the unique pointer constructor for a raw pointer. So I mean, there are a number of different approaches that you could take, which would be much less, would require people to type much less if you could then like consistently go for the convention that every raw pointer that you see is non-owning.
Right. Right. So that's probably true. And I don't want to be prescriptive for anyone else's code base. Like I said, one of my theses though was I think being explicit is better than implicit. If I only have essentially 2 owning smart pointers and 1 non-owning smart pointer, I've added very little extra overhead mentally to have that non-owning smart pointer instead of a raw pointer. And I can construct cases, and we have them in our code at least, where I have to have a raw pointer that actually has ownership. Because I can't use atomic updates on move-only types. They require copying, and copying can only be done with raw pointers.
But wouldn't it be better to fix these cases so that in the end you would end up with a code base where you actually don't have any valid use case for a raw pointer except for it being unowned, and then you could just go for the shorter and nicer syntax?
Well, I'm not sure how I'd fix that. I have to use a raw pointer because I need atomic updates. I need atomic updates because I'm in a lock-free programming system. I happen to be. You may not be, in which case, yes, you can probably much more easily move to that world where you just say, look, it's a raw pointer, it's non-owning. I can write some tooling that says don't type delete or other things. Unfortunately, you can't get rid of the constructor for unique putter that actually takes ownership from a raw pointer. That's just in the C++ system, and the committee is not going to get rid of that either, I don't think, anytime in the next 50 years. So, but yeah, there are definitely other options possible. I think this is the way we've gone. Thank you. Any other questions? All right, well, thank you very much for your time.